Hello everyone. I hope everybody doing good. So today we are going to see about the topic called multi-core or multiprocessor architectures, which is one of the important architecture in the field of computer organization. So before going to start the explanation, so let us see one small example. We just consider we are having one job. So the particular job can be done by 10 peoples. Suppose you consider a man can do a one day work. So if 10 persons are involved and if they did the work in series, there will be a 10-day work to be there will be a 10-day works to be done, which means it will take some 10 days to complete the work. But if they done the work in parallel, it will take only one day. So that is the concept of this multi-core architecture. So one person can do one work. So totally 10%. So it will be taking 10 days. But if suppose one person they are doing one work and then they are going to do in 10% are going to do on the same day. So it will be taking only one day. So that is the concept of this multi-core or multiprocessor architecture. So so here what we can observe, we can increase the speed, we can reduce the time because we reduce to 9 days. Then the performance of our system also got increased. And then one more thing also we can consider here, the manpower simply it is the power consumption that is simply not utilized, simply not wasted. So that is the concept of this multi-core architecture and multiprocessor architecture. So let us see the agenda of this topic. So today that is we are going to see about introduction and why we are going for multi-core architecture in terms of power and performance. Then the various multiprocessor architecture which is available today, and we are going to conclude with the multi-core architectures. So let us see the introduction. So if there are some never-ending story which is available, that is complex application, which means day to day we can able to see the application level is getting increases. Okay, so people are incorporating artificial intelligence, the machine learning, and Internet of Things. So many things are added. So the complexity of our application is getting increases. So this is never-ending story. Later in coming days also the complexity will be getting increases. And then everybody wants faster computation. So faster computation. And then so these two things how we can achieve with the help of Unicore processor. So Unicore processor in the sense that is a single core. In that you will be having only one core. You can execute only one instruction at a time. In previous session we discussed about instruction execution cycle. So that will be executed only at a single time. So that is what Unicore processor. So to overcome these limitations, we can come with some parallel processing. Okay, so parallel processing in the sense what? As I said in the example, the people are going to do in parallel. So which means we can reduce the performance and power. So that is the concept over here. So parallel processor plays a vital role, and then we can improve the performance. Okay, and then so we can overcome the ILP exploitation, and then the embedded software we can have some parallelism. So we can go with some attraction about multi-core processor. So that is due to slowdown of advanced UNI processors. So nowadays we can able to get in India we are getting some multi-core processor, that is Intel i3 processor, Intel i7 processors. Even in mobile phone also we are getting some multi-core processor, quad-core processor. So like that we are getting different processors. Okay. So while coming about the level of parallelism, so during 1970 to 1985, people worked about bit level parallelism. That is 4 bits, 8 bits, 16 bits, 32 bits. So like that bit level parallelism they did. And then from 1985 to till date, the instruction level parallelism is one of the major role. That means in previous class we discussed about instruction cycle, that is fetch, decode, execute, result, store. So like that, there are some different stages are there. So those stages we can do through pipelining. So that is one thing. And then another one concept that is in instruction level parallelism, that is about superscalar and VLIW and out of order execution and dynamic instruction scheduling. So like that, we have different instruction level parallelism mechanisms are there. And then in the next level, they come across with software that is process level or thread level parallelism. So we all know what is process. So process is nothing but a program in execution. Okay. So we can have multiple processes. So those multiple processes can be executed in parallel. So for that, we will be using different servers are parallel and desktop dual processor PCs and multi-core architecture. So with the help of these things, we can able to do process level or thread level parallelism. So like that, we have different levels of parallelism. One is about bit level parallelism, another one is about instruction level parallelism, then third one is about process level or thread level parallelism. So while coming about the architectures, we have some 4 different types of architectures. So one is single instruction, single data, that is uniprocessor, and multiple instruction and single data. So it is about multiprocessor on a single data stream, and then single instruction, multiple data. So that is also a kind of parallelism, and multiple instruction and multiple data. So here only we have to give some more concentration. So here the parallel operations comes on the MIMD architecture. So some examples of MIMD architectures are Sun Enterprises 5000, Cray T3D, SGA Origin. Okay, so these are all some examples of MIMD architecture. So while coming about MIMD, there are 2 types are available. One is centralized shared memory unit multiprocessor, and another one is distributed memory multiprocessor. So in both level, we can able to achieve what thread level parallelism, and then we can able to do some different types also available, that is independent programs and parallel iteration of loop. So centralized memory architecture is given here. Here the memory is common, but the processor is different. So here we can able to see here that is here we have here we can able to see this is processor 1, processor 2, processor 3, processor 4. Okay, and then here each and every processor having their first level of cache. There is one or more levels of cache will be there. Then here we can able to see this is the centralized memory. So the memory system will be common, but the processes are different. So that is called as what centralized memory, centralized shared memory multiprocessor. And then the IO systems also common. And while coming about the distributed, we can able to see each and every processor. Okay, each and every processor will be having its own memory and its own input-output device. So here you can able to see this is processor plus cache, memory and IO devices. They are connected with the interconnecting network, or we can say as network on chip. Okay, through that we can able to connect it. So here we can able to see in a distributed memory multiprocessor, will be having everything in a separated way, and they can be connected through this NOC or interconnect network architecture. So this is the difference between distributed memory multiprocessor and centralized memory multiprocessor. Okay, so there are some different approaches for data communication. One is distributed shared memory architecture, and another one is non-uniform memory access, since the access time depends on the location of the data. So next, while coming about here, one important thing about this distributed memory architecture, there will be some cache misses are available. So those caches are the sources of the caches are what compulsory misses, okay, capacity misses. The compulsory misses that will be happen at the cold start, that is at the beginning, and then capacity misses that is due to finite cache misses, and conflict misses that is due to the collision misses, and coherence misses. So these are only 4 misses of caches. So we have to provide some solution to that. So that is not needed for right now. So so these things can be applied to the graphical processing units also. So this is one example of multi-processor, that is graphical processing. So here in graphical processing, we can able to see we'll be having some GPU onboard RAM, and then here we'll be having different processors, and each processor will be having different n number of processors. Okay, so like this, as this is one example of centralized architecture. Okay, so they are using SIMD model. Okay, so this is one type of parallelism. Okay, and while coming about NVIDIA CUDA hierarchy, so there we can able to see different grid level kind of architectures are available. So in grid 0, grid 1, grid 2, so multiple threads will be coming, and that will be executed. This is NVIDIA CUDA architecture, and then some GPUs about NVIDIA. So here we can able to see there will be some memory controllers, and then here you can able to see the green color which represents your processing unit, and then here you'll be having some engine, processing engine, everything will be available. Okay, and this is about the specifications. So what about the memory size, what about the clock size, okay, and memory input output, memory configuration. So everything is available on this NVIDIA Tesla GPU board. And this is about another one kind of board, that is NVIDIA Maxwell GM100. So it is having 8 GB of RAM, and 114 cores are available. Here you can able to see the number of cores are 114. That means we can able to execute multiple cores on a single chip. Okay, so this is another one kind of GPU. So the problem is it is designed for graphics rendering, and it is not designed for general purpose computing. Okay, so that is earlier thing. Now people are working about general purpose computing also. And then here the memory hierarchy is local memory and shared memory and global memory. And then here we can able to check the data movement cost also. That is very costly, and it is not optimal one. So these are all some problems. Okay, and to increase the speed up, they are doing some parallel work. So the speed up we can able to calculate with the help of 1 divided by 1 minus p plus p by s. So where p is the fraction of program that is in parallel, and s is the fraction of program that is in sequencing. So this is what the AND does now. That is, we can able to see the number of processors and speed up. So while we increasing the number of processors, the speed is about to getting increases. Okay, so that is what this AND law describes. Okay, so here we can able to see if we are increasing the number of processor about some 8192 core, that is we can able to increase the speed of some 20. Okay, so the parallel portion got increases. Okay, and then here one example of multi-core CPUs. So here you can able to see we'll be having some RAM, core, and then level of cache. So everything will be available. And some example of multi-core CPU, that is Intel Nehalem processor and Intel Xeon processors, and so many multi-core processors are available. So Intel Xeon processor, that is from the 2001, it is being available, and it is widely used in workstation and laptops. Okay, and heat dissipation is one of the major problem. So that problem nowadays we can able to reduce with the help of some cooling system. And Intel multi-core CPU performance is given here. That is, I have taken the data for 2001 to 2010. So while we are increasing the number of core, the speed is about, we can able to see in terms of 55x it is getting increases. The speed is about increasing in terms of 55x. So that level it is getting increases. In concluding to this topic, so we discussed about parallel mechanisms and parallel solution, and inherently sequential program don't benefit much more. So two main types of parallel architectures, that is SIMD and MIMD, and modern parallel architectures are GPUs and some CPUs that is coming with the multi-core architecture, that is Intel Xeon and Intel Nehalem processors. So that's all about this multi-core architecture and multiprocessor. Thank you all.